Hi, I'm Carleton Coffrin, and it's my pleasure to be speaking at JumpDev2021 about the infrastructure modeling packages that we've been developing in Julia as part of a JUMP extension. Just to set expectations, I'm going to warn you this isn't going to be a deeply technical talk. I will give you some details of how we're engineering this software, but the goal of this talk is to really give you the motivation for why we're building these packages and where we're at and where we've come in the past 5 years. So let me begin with a little bit of motivation of what's going on in the broader world. It may be obvious to many, but we're in an era of transformation for critical infrastructure systems. We're seeing dramatic changes throughout the world, which is resulting in new reliance in our critical infrastructure systems. So, for example, if you think about 50 or more years ago, we had electrical devices like these, lights, refrigerators, air conditioners, and televisions, where now we have things like computers and cell phones and electric cars are becoming more mainstream. So our dependence on the energy sector is increasing quite a lot. On top of this, we also have more dynamic conditions in power grids. So for example, we have rooftop solar being adopted by many residential folks. We have electric vehicles entering the market, which is dramatically changing the load profile of energy throughout the world. And we have things like massive renewable energy farms, like the wind farm you see pictured here, that are also changing the way we use our critical infrastructure and energy specifically. What you're seeing in the lower right is often referred to as the duck curve, and this shows you how over time the usage of energy throughout a typical day has been changing in California. So the green lines indicate the way it used to be, where it was kind of flat and then with a peak around the evening time. But now what we're seeing with the introduction of all these new technologies is that there's a big dip in the middle of the day and then an extremely fast ramp up at the end of the day. So these conditions are much more dynamic than people have usually been planning for. Another big change are the increasing disruptions we have from extreme events like hurricanes or ice storms, which were common before, but maybe are increasing in frequency now. But we've also seen recently the effects of wildfires at different places throughout the world, and increasingly the threats from cyber attacks to critical infrastructure systems. So all of these changes kind of come together and add up to being a really big critical question for us as a society, which is how can we design and operate our critical infrastructure networks to improve their resilience in response to this more dynamic and disruptive world. This is a really big open challenge that I think we're all facing around the globe and in the United States as well. There are many big picture ideas being proposed for how we might address all of these things. One of them is called gold plating the grid. So the idea here is that we just build a lot more infrastructure to handle increased dynamic conditions and increased resilience. This is following current best practices, but it's a kind of on steroids because it would require a ton of additional investment. Another proposal that's out there is to build lots of large-scale storage. And the idea here is that we can kind of smooth out or ignore the uncertainty that's in critical infrastructure networks if we had a lot of storage on the side. Also a very reasonable approach. There are also even more radical proposals out there. So for example, right now the critical infrastructure networks are designed in a hierarchical fashion where you have huge facilities that are then trickled down to individual users, and we could change that to a more meshed network design where you have more like micro systems of critical infrastructure that are self-supporting, but then borrow and trade resources to neighbors when times are good or you don't need the resiliency criterion. So this raises some major questions, like how can we renovate our current critical infrastructure networks and operate them for this next generation? I've proposed for you 3 ideas here, but there could be many of ideas. There could be hundreds of different approaches. And in reality, probably a bunch of different approaches will be used simultaneously, and they'll all come together to give you more resilience and more efficiency in this changing world. And then, of course, we want to do this all at minimal cost. That is one of the reasons why this gold plating approach isn't already underway, because the costs to do that are quite astonishing. And this is where I believe operations research really can come to the rescue. We want to design a new infrastructure system. We want to operate it more efficiently. All of these at minimal cost or maximal resilience. These are the kind of core tools that operations research can help you with. So this was a big part of our motivation for building this infrastructure packages, was to bring OR to these critical infrastructure challenges. Now, a holistic infrastructure modeling system is really a grand undertaking. So for example, if we look up the Department of Homeland Security's website, they identify 16 critical sectors for the functioning of the US government and economy. They have things like telecommunications, transportation, energy, and water. And there's, 11 more of these or 12 more of these that you could consider. Let's just think for a moment hypothetically about what it would take to really have a holistic energy modeling solution. We'll begin our inquiry with some power generation. You could think of things like coal-fired power generators or nuclear power generators. They provide a huge amount of the base load in the US network. Then, of course, we need the consumers of this power. So we're going to need to model some homes and some electric vehicles, for example. And then how does the power get from these huge generators down to these consumers of the power? You have a transmission network that has been engineered over 50 to 100 years to carry this energy across. But that's actually not enough, because you have these smaller poles and wires called the distribution network. To actually get all the way down to the homes and to the cars, you would require to model this as well. And at this point, you're kind of in a reasonable spot where you have the sources and the sinks of energy. You could start to model the whole system. But then folks may come along and say, hey, what about rooftop solar? Like what impact will that have on the grid in the next 10 or 20 years? And then you realize that to model this, you need to also incorporate the fast ramping gas power generators that currently support the dramatic changes that we have in solar power. And to model these, you need to model the gas network. And if you're going to model the gas network, you need to model compressor stations, and so on and so forth. And you kind of go down this rabbit hole of needing to model the entire world before you can start to answer, what are these, how do we solve these really massive challenges for how to run the energy sector or other critical infrastructure networks. They're all interconnected. So several years ago, we started this Power Models project in Julia, really as an experiment to see if we could use Julia and JUMP to solve these kind of critical infrastructure challenges. So I mentioned we started this in 2016. This was my first kind of delve into JUMP and Julia development. And we even presented the Power Models framework in JUMP Dev 2017. You can go and view the video on this YouTube link if you're curious. And in that particular experiment, we were wondering, is it really possible to use Julia and JUMP to build commercial-grade power transmission optimization software? And could that become the core of our research platform for conducting research at Los Alamos National Laboratory? And so this was very much an experiment and an open question, and the focus was therefore very narrow. We were looking at power transmission networks, just a small piece of the whole ecosystem that I was just describing. So I'm going to begin by giving you a little update to where we are with this experiment, and then how we've generalized it to support other infrastructures. So one of the big questions on my mind was performance. A lot of people want power network modeling tools to scale to incredible problem sizes and still be state-of-the-art in terms of performance. And this was a big question both for Julia and for JUMP. How could we scale? How far could we go? And for me, this project that I did recently, and it's still ongoing with ARPA-E, which is called the Grid Optimization Competition, was a fantastic test of the scalability and performance of JUMP and Julia and this Power Models framework. In this particular competition, you have to solve optimization problems with 1 billion to 5 billion decision variables if you were just going to write them down in a naive way with a comparable number of constraints. And usually you want to solve this in 5 minutes or less. So this is really well beyond what commercial tools do, and it's an incredibly challenging optimization problem. That's why it's pushing the frontier of science and industry. So as part of this activity, I've built Power Model Security Constrained, which is focused at this class of optimization problems, and we fared very well with that algorithm. So we've finished 10th in the first challenge. Currently, we're ranking between 2 and 4th in the second challenge. But the particular rank is not too important to me. What is very exciting is that we were able to scale this software to run at near highly competitive performance to all the other solutions that were out there, which really convinced me that you can make incredibly performant code in Julia and Jump. For the second dimension, could this be a research platform? We've started to see a number of packages grow around Power Models that show this has been a success. So if you're interested in transmission network storage, we have some proof of concept examples that are available. If you're interested in transmission network vulnerability and resilience, we have a package for that now. The impacts of solar storms is also being studied using a Power Models extension. And there's a variety of other smaller explorations that are being conducted in this Power Models Annex project. So this has been a great success for our research agenda and has really been succeeded on that dimension of the open question. Another thing that maybe wasn't a goal of ours, but has been very encouraging, has been the adoption of Power Models in the broader community. So in the past 5 years, we've had 69 releases of Power Models. We've had 194 stars on GitHub. We're typically seeing about 150 unique visitors in every 2 weeks, and there's been a number of contributors that were not LANL staff, which suggests they're finding this useful in their research and they would like to give back to the package. Oscar had done a survey of different downstream packages, and he told me that it's okay to claim that Power Models at this time is the most popular Jump extension because of how much stars and other metrics it has. I recommend you talk to him exactly how this is calculated, but I'll happily take that accolade. When we released Power Models, we also published a paper about it and really emphasized its ability to explore different ways of formulating interesting optimization problems. And since that paper was published in 2018, it's received 100+ citations, which is also a big success for a publication. So all in all, I think the Power Models experiment was a great success and showed us at LANL that Julia and Jump, we could really commit all in to a solution for our research needs and our deployment needs. But there are still a bunch of limitations for Power Models. So if you want to understand in a lot of detail distributed energy resources and you want to look at how we could solve this duck curve problem, you need more power distribution modeling than what was available in Power Models. If you're interested in cascading effects from, say, cold snaps that can occur between the natural gas system and the power system, you need to model the national gas transmission networks. And just going back to the original motivation of this talk, we were wondering if we want to solve these really big open challenges, can we extend this Power Models idea to other critical infrastructures? And more importantly, can we make it easy to integrate multiple infrastructures together and solve multi-infrastructure optimization problems to answer these more deep questions about our energy future? So this is the introduction of infrastructure models, which is really the whole ecosystem we've been building for several years around the Power Models idea for multi-infrastructure modeling. So if this was what the picture looked like in 2016 when we started Power Models, this is what the picture looks like now. We have infrastructure models, which is a general package that includes some basic guidelines for developing different infrastructure sector packages, and we've expanded to include power transmission, power distribution, petroleum networks, natural gas transmission networks, and water distribution networks. And of course, we couldn't do this just alone by myself. The team of developers on this project has grown to 5 core developers, including Russell Bent, David Phobes, Karthik Sundar, and Byron Tassif. The code base, when you sum up all these different packages, is around 85,000 lines of Julia code and represents thousands of hours of labor from all these different folks and other folks at LANL. So it's really been a massive investment. This project has touched on a lot of different programs at LANL, and we actually received a Distinguished Performance Award in 2019 for the impact it's had on the whole research agenda that we've been doing at LANL. So it's really quite a massive project at this point. I'm going to give you a bit of the theme and the design of this broader ecosystem, and then talk a little bit about how we integrate them. So what is the theme of infrastructure model packages? The goal here is to have infrastructure-aware, JUMP-like modeling layers. So we're going to take JUMP and we're going to specialize it even more to critical infrastructure systems. Additionally, we have minimalist MATLAB-like data formats that are really useful for R&D purposes, but we also develop parsers for established data files like PSSE is an industry format for power transmission. MapPower is a popular academic format for power transmission. We have GasLib, which is for gas network R&D. We also developed our own MatGas format for gas transmission networks and a MATLAB type of design. We also support things like OpenDSS and EPANet, which are industry standard formats for their respective sectors. And then across all these infrastructure modeling packages, we have certain standards in how the code is organized and how the data is organized. For example, there are lists of components that are organized by component type. Each component has some standardized universal fields like an index, which is a unique integer ID, a status, which tells you if the component is active in the current analysis or not, a name, so you can give them a nice textual name for display purposes. And the goal here is that all of these packages independently on their own would feel very similar in how you use them. So that if you pick up one infrastructure sector in this ecosystem, it would be fairly easy to reuse that knowledge to pick up another one. And then our secondary goal was to make it easy to integrate these, and I'll show you an example of that a bit later. So I'm going to give you a sense of what all these packages are like with a simple optimal power flow study using the original Power Models package, but rest assured that the workflow would be nearly identical regardless of what sector you're using. So you begin by installing using the Julia package manager, so you do package add Power Models. You're also going to need a mathematical programming solver because we're just build jump models, we don't actually solve them. So in this case, we'll pull in IPOpt as an easy, flexible example. Then you pull in the Power Models package. You use functions like parse file to read those nice, convenient data files. There's a print summary function, which will print the data in a human readable format. And then you can dig into the data item by item using a nested dictionary dereferencing. If you want to solve a classic optimal power flow problem, you bring in IPOpt, and then you call these helpful functions like run ACOPF or run DCOPF. You give it the network data and the optimizer, and what it does is builds a jump model for you, encodes the problem, solves the jump model, and then decodes the answer into a solution data that is standardized across different infrastructure model packaging. So you can see when you do print summary AC result solution, this is going to give you the solution data that's re-encoded into the data standards of these packages. Digging a little bit deeper into this, let's look at what the data structures look like. So if you do parse file with this MATLAB file, the source information is in a textual matrix-like format. So you can see here that I'm showing you the MATLAB raw text below here. It has a function name, it has some values defined, it has some matrices defined, like a bus matrix and a branch matrix. When we load this into Julia, we've converted it into a dictionary. So now we have a dict, which has a nested structure, but with the similar names like bus and branch and line. And then if you want to look up specific values in these tables, there's a very consistent way where you say the data, the component type bus, the component ID 1, the voltage magnitude is called VM, and you get the value 1. So on, the similar is true for branch 3, BRX, and then you get this value 6004. So we start with this data as dictionaries, and that's one of the core pieces of all these infrastructure modeling packages. Now, I mentioned under the hood, there's a jump-like modeling layer for infrastructure modeling. And so this is what it looks like. So build OPF is like a model building function that's going to build you a jump model, but all of these functions are specialized to understand the infrastructure you're working with. So you have variable declaration, which is defined over things like buses and generators and branches, which only makes sense in the context of a power network. We have our objective function, which in this case is fuel cost, though you could have other ones. And then we have our constraints. The key point here is that you have things like what are the IDs of the buses and the branches that allow you to do component-wise constraints across the different components that are in your network. So then this raises an interesting question. How do you support multiple infrastructures if each infrastructure has its own jump-like modeling layer? And in the past year, Byron Tassif has been working very hard on making a beautiful implementation that allows us to do these types of combined algorithms. So we have this package called gas power models and also power water models that combine these. And the big question is like, what does this build gas power flow problem look like? And the beautiful thing is that it mostly just delegates to the sub packages. So for example, in this case, we've developed a way where you can just say build a gas flow problem, and here's like the jump model you need to add it to. And so this package doesn't know anything about the broader ecosystem. Then we can ask, build some power flow problem, and only the power package knows how to do that properly. And then in the last step, we do these linking constraints that connect the two pieces. So we're able to build a gas power model package which leverages all of the complexity that's in each of the dependent packages and then links them together with the minimum amount of information. So what is the key to this integration? The first piece is the composability of Julia functions. The second piece is that mathematical programming in JUMP provides us a beautiful and consistent way to encode mathematics across all these different packages. And then the last piece is that we have a standardized data store so everyone knows where to put their data and it doesn't clash. So in infrastructure models, all the structs have a similar structure where you have things like data, you have the solution output, you have your jump model, which people can share, you have your jump variables and expressions, and then you have your constraints. And the key thing is for each one of these dictionaries, there's a unified structure for where everything goes. And it looks like this. You have an infrastructure type, you have a network ID, you have a component type ID, you have the components ID, and then you have all the fields of the components. And depending on what it is, it might be a float, an int, a string, a variable, a constraint. So here's an example from one particular package where you just have like the infrastructure type for power models, network 0, generator 1, and then the active power constraint, PG, or variable, PG. So if I was going to return to the start of this talk and ask the question, how can we design and operate our critical infrastructure to improve its resilience and response to a more dynamic world? We have proposed infrastructure models to help with this question. Ultimately, national policies and regulations play a major role in what's possible, but policymakers are always looking for innovative technical solutions. And we hope that infrastructure models provides this foundation to explore rapid, different approaches to these innovative technical solutions. And we hope that this will inspire folks in the community to come up with good ideas that could actually be implemented in practice and have a real big impact on the world. We're currently using infrastructure models for providing situational awareness, so it's a real tool that's being used. So I'll just conclude by giving special thanks to a couple of key folks. Of course, we have the core LANL developers. This would not be possible without them. There's been some early adopters and super users from KU Leuven and Energyville. Frederick Geth and Hakan Ergun have done a fantastic job joining the community. And then there's a bunch of external collaborators that have had a huge influence and been really helpful in building the ecosystem. With that, I thank you very much for your attention, and I look forward to any questions that you may have about infrastructure models. Please feel free to reach out and ask me and give us feedback. Thanks a lot.